In this lesson, we're going to learn about Charles' law. So this law is a relationship between volume and pressure, and Charles found that when we have a certain amount of gas and the pressure is kept constant, he found that the volume and temperature were directly proportional as long as temperature was measured in Kelvin. And we're going to take a look at what that is. So before that, we'll take a look at a simulation. So pressure is kept constant, so I'm going to keep the mass that I have on top of this lid the same. And I'm going to change the temperature so I can see that at a low temperature, the space or volume taken up by those particles is quite low. And as I increase the temperature, I can see an increase in the volume occupied by those particles. So I can also see that those particles, as I lower the temperature, vibrate slower, so they have less kinetic energy. And as I increase the temperature, they have more kinetic energy and vibrate faster. So I can see here, as well as I am increasing the temperature, the volume is also increasing. So Charles found then that the initial volume divided by the initial temperature in Kelvin was going to equal the final volume divided by the final temperature in Kelvin. So he used this to learn about the Kelvin temperature scale and to come up with a theory there. So this shows us for 1 gram of oxygen at different temperatures what volume that oxygen would occupy, for 1 gram of carbon dioxide and half a gram of oxygen and half a gram of carbon dioxide. So because Charles found linear relationships here, what he did was, with his line of best fit, he extrapolated his data and found that all of the lines came to a point at negative 273 degrees Celsius. So the absolute temperature is based on an idea that eventually at some temperature, all kinetic motion is going to stop. And that was over here. So we saw that as the gases had less temperature, they had less kinetic energy, and they took up less space. And so we can see all of these converge here at negative 273. So the theory is that at that point, there's going to be no movement of the particles, not even a back and forth vibration. So that is known as absolute zero. And that happens at negative 273 degrees Kelvin, negative 273 degrees Celsius, and that is equal to 0 Kelvin. So that is the Kelvin temperature scale. Each unit, each Kelvin, increase or decrease is the same increase or decrease as 1 degree Celsius. So from 0 Kelvin to 1 Kelvin is negative 273 degrees Celsius to negative 272 degrees Celsius. So the increments there are equal. So the actual amount is 273.15. So to convert to Kelvin, you take your degrees Celsius and add 273.15. And if we're using 3 significant digits, which we generally will here for a temperature, we have 273 that we'll use. So to calculate degrees Celsius, we'll take an amount in Kelvin and subtract 273. And the reverse, if we're looking for Kelvin and we have Celsius, we will add 273 to that. So really important is that with the gas laws, any of the gas laws that include a temperature must have that temperature in Kelvin. So we have to use the Kelvin temperature scale for the gas laws. So Boyle's law, which we looked at, had a constant temperature, so temperature was not involved in that relationship there. So let's do a couple of conversions. So 573 Kelvin. So if I want to convert that to Celsius, I'm going to take the 573 Kelvin, subtract 273, and that will give me 300 degrees Celsius. 39.6 degrees Celsius, so to convert to Kelvin, 39.6 plus 273, which is equal to 312.6 Kelvin. So each time before we use a temperature in a formula, we have to do this conversion from Celsius to Kelvin. And then at the end, if we are asked for a unit of measure in Celsius, then we will have to do this conversion. So an example, if I have a gas sample at 40 degrees Celsius that occupies 2.32 liters, if the temperature is increased to 75 degrees Celsius, what would be the final volume? So to start with, I know the temperature, 40 degrees Celsius, add 273 to convert to Kelvin, so that's 313. My initial volume, 2.32 liters, and final temperature is 75 degrees Celsius, plus 273 is equal to 348 Kelvin. So these are just all those pieces of information. Here's our relationship between volume and temperature. And so we can fill in the values that we have. And to solve for the final volume, this is divided by 348 Kelvin. So to do the opposite of that, I'm going to multiply by 348 Kelvin. And when I calculate that, my final volume is going to be 2.58 liters. And we can use unit factor method just to make sure that we have everything in the correct place. So my Kelvin cancels out and my answer is in liters. Another example. So I have a gas at 100 degrees Celsius that occupies a volume of 2.32 liters. What's the temperature change in degrees Celsius if the gas expands to 5.61 liters? So I know my initial temperature is 100 degrees plus 273 gives me 373 Kelvin. Initial volume is 2.32 liters. And final volume is 5.61 liters. So I can calculate my final temperature for this, but I'm asked for my change in temperature. So once I have my final temperature, I'll have to look at the difference between that and my initial temperature for the temperature change. So these values here at the top, there is my formula. Now, because I'm looking for a temperature, I can rearrange this to have temperatures on the top. So as I plug in my values here, to make it simpler for yourself, if you had started with this, then you would have 373 Kelvin over 2.32 liters equals temperature final over 5.61 liters. And then this is a division by 5.61. The opposite would be to multiply over. So temperature 5.61 liters times 373 Kelvin divided by 2.32 liters. And we've got canceling of our liters. Our final answer here is in Kelvin. So that's 902 Kelvin. Now we weren't asked for the final temperature. So 902 Kelvin, if I subtract 273, is equal to 629 degrees Celsius. I was asked for the change in temperature in degrees Celsius. So if I started at 100 and ended at 629, that is an increase or a change in temperature of 529 degrees Celsius. Now what you will notice, because each degree Celsius is the same as a degree or a 1 Kelvin, the difference between 902 and 373 would also be 529. So you don't actually have to convert back to degrees Celsius here. You just have to make sure that you are doing your subtraction either with both Kelvin or both degrees Celsius.